Beautiful. Okay, we are going to continue on the Taylor series and then show some really cool applications today. First one I want to do is I want to develop the Taylor series for a really, really nasty one. All right, we consider f of x is the inverse tan. This is actually considered a pretty important one, but of all of the ones that we deem important, like e to the x, sine x, cos x, and log x, those are the other biggies. We've done most of them. This one here is a little bit nastier because I have to take multiple derivatives. And after the first derivative, the derivatives can get really nasty really, really fast. So what we want to do is we want to find the Taylor series for this expanded about 0. Because I can evaluate the inverse tangent of 0, and I can take all of the derivatives and evaluate them at 0. So 0 is practical. So you write down the first few, okay? So the first derivative we know is just going to look like this. That's easy. And then the second derivative, that's not too bad. That's just going to be negative 2x over 1 plus x squared. Squared. I don't have to do much. But now the next few derivatives, I have to use product or quotient rule, should use product rule, and chain rules and stuff. So I went ahead and did them for you to save ourselves some time. So the third derivative is 6x squared minus 2 over 1 plus x squared to the third power. The fourth derivative is, let's see, negative 24x to the third power plus 24x over 1 plus x squared to the fourth power. And I'll stop at the fifth derivative. And the funny thing is, I checked these through doing them on Wolfram. And they'd say Wolfram had the wrong fifth derivative. In fact, it was, if you go to Wolfram and look at it, go, that doesn't even look like you asked the same question. Yeah, I'll give you a hint. You want to guess the exponent there? What do you think?
X to the fourth plus x squared.
Fifth.
Oh.
Yeah, fifth power. Okay, and then on top it's going to be 120x to the fourth minus 312x squared plus 24. We've got enough now. We can keep going. We can keep going. The funny thing, Wolfram, I was doing, gave, I believe, 6 quotients. He gave the sum of 6. I think it did sort of like a partial fractions decomposition because all the quotients had different denominators, which really isn't very useful. Now, I'm evaluating every one of these at 0. So the evaluation's the easy part. It was the derivatives. Now, we can keep going, but you're never going to see a general pattern for the derivatives. But I'm not looking for a general pattern of the derivatives. I'm looking for a general pattern of the derivatives after I evaluate them at 0. That's the key. So let's consider f of 0, f prime of 0, f double prime of 0, f triple prime of 0, fourth derivative of 0, fifth derivative at 0. And hopefully, we can see a pattern for maybe the nth derivative at 0. Maybe? All right, so let's evaluate these. All right. The inverse tangent of 0 is, that's one we should know. Tangent of what angle is 0? Remember, inverse tan returns the angle. The tangent of what angle is 0? 0. Yeah, that's kind of an easy one. Should you know that one? Yeah, like about the third or fourth day of a trig class. That's kind of like saying when I ask what's the cosine of 0, I really don't want to hear 0 as an answer. I really want to hear 1. Believe it or not, 50% of all calculus students still can't do sine and cosine of 0, which is scary. And tangent of 0 is 0. Okay, now f prime of 0? 1. F double prime of 0? 0, huh? F triple prime of 0, the bottom's going to be 1 every time, isn't it?
Negative 2.
So negative 2. Fourth derivative of 0.
0.
That's kind of weird. Fifth derivative at 0.
24.
24. Anybody want to go out on a limb? What do you think? There is definitely a pattern, and we have done enough to see a pattern. Tell me one pattern, clearly.
Even derivatives are zeros.
The even derivatives are zero, not the odds. So I'm going to write it like this. Oops. That is definitely the case. So it looks like only the odd derivatives. Now the original function would technically be considered the 0th derivative, okay? So here's what we're looking for, the n plus first derivative. Well, let's see, I don't see a pattern there, but maybe 24. Wait a minute. I see 2s, I see 24. Where have we seen 24? Anybody know? I'll give you a hint. In this context, you only see 24 in one situation. And it's the same situation over and over and over. There is only one mathematical calculation that will produce the number 24 in this context. It's 4 factorial. That's one we really want to know. 3 factorial is 6, 4 factorial is 24. After that, they start getting harder to remember because they get kind of big. I want to work backwards. This is 4 factorial. Oh, what's 2? Wouldn't that be 2 factorial? But it's the negative of 2 factorial. Then what would 1 be, do you suppose? 0 factorial. Do you see a pattern since I'm going every other term? What do you think the 7th derivative evaluated at 0 is going to be?
Negative 6 factorial.
The negative of 6 factorial. That is exactly the pattern. Everybody see that? I really don't want to do the 6th and 7th derivatives because that 5th derivative took me long enough this morning. I don't really want to do more. So Ryan, that's what I did after you left. So what does it appear to be? Well, clearly they're alternating in sign. So at the beginning, it's a 0 factorial. So when my n is a 0, I should be 1. So this is definitely going to be negative 1 to the nth power, because now that would be 2 times 1 plus 1, third derivative. That would be 2 times 2 plus 1. So the even derivatives, excuse me, the even values of n, okay. The factorial is 1 less than the derivative. You with me so far? That is the pattern right there. Now, if you remember, I showed you guys the other day that the Taylor series is, we started by writing it this way. Our c is a 0, so we can ignore the x minus c, but that's what it is in general. So I'm going to write x to the n. And then what did this guy end up being? Do you guys remember? You should have it in your notes. It's the nth derivative evaluated at c, which in this case is 0. So I'm just going to make that c into a 0, over n factorial. Now what do we have? We have the 2n plus first term. So we're not going to have an n, we're going to have a 2n plus 1 in our formula. So let's go a step further. This is a n. So what would a 2n plus 1 naturally then be? It'd be the 2n plus first derivative evaluated 0 over 2n plus 1 factorial. Have we just figured out? Yeah, we just figured it out. So for this problem here, what will this be? It'll be negative 1 to the n 2n factorial over 2n plus 1 factorial. Do I get any canceling here? Well, let's see. 2n plus 1 quantity factorial, isn't this 2n plus 1 times 2n factorial? In which case, I get a lot canceling, don't I? That's just going to be negative 1 to the n over 2n plus 1. That's not that unfriendly. So going all the way back, we have just figured out the Taylor series for the inverse tan. This is how it's done, by the way. There's no shortcut to what I did. This is how it is. Kind of yucky. So this is the summation, -1 to the n, 2n plus 1, x to the 2n plus 1. Okay? Now, let's pull out our old friend Desmos here. Oops, hold on. Let me enter that real quick. Y equals oh, it's not like this. Okay, let's go with this. Okay, there we go. You'll accept that. I'm going to erase this stuff in the middle. I'm not sure that this board is going to let me pull it down. Let's see, I'll try this. Usually this is sort of a dead-end proposition, so I might just go with just go with this. Okay. I think we can all see this.
This is right. You could also try dimming the light for the front.
Yeah.
And then-
Do I want to bubble off?
Yes.
Can everybody see that clearly?
Yep.
Yeah.
Okay. I don't like doing it this way, but that screen is so hit and miss. As long as you can see it, 'cause that's inverse tan. Okay, great. So let's do the first few terms of our Taylor series. Now, what would the first few terms be? Okay, let's just play it. So when n is 0, what do I have? When n is 0, I have what? Just
1 over 1.
times x to the first power?
Yeah.
Okay? What's my next term? So when n is 1, I'm going to have an x cubed. I'm going to have a -1/3 x cubed. Everybody see that? It's pretty easy to see the pattern at this point. So x third over 3, then what's the next term going to be? Plus
X to the 5th.
x to the 5th over 5.
Minus
Well, those look totally different. Yes, they do. Minus
X to the 7th.
x to the 7th over 7. You see anything happening here?
We're getting closer and closer in the range where like they follow each other.
Now, that's -2, so this is clearly what, -1 to 1?
Yeah.
Can everyone see them from -1 to 1? They look spot on. I mean, I really can't see a difference. And let's get out our calculators. I'm going to just go that way for now. That's 4 terms. Let's get out our calculators, and what I'd like to do is let's take a value that's really small. How about 1/2? Let's calculate the inverse tan of 1/2. And by the way, what do we call this guy here? Do you remember there's the notation?
P7.
That would be P7, good. And that would be x minus 1/3 x cubed plus 1/5 x to the 5th minus 1/7 x to the 7th. I would like to find P7 of 1/2 or just 0.5. I would like to find the inverse tan of 0.5. Now make sure you're in radian mode, by the way. Make sure you're in radian mode. And let's do both of those things because we just want to demonstrate this is the power of a Taylor series. That I can use a polynomial instead of the transcendental function, which is just crazy to think about it, okay? All right, so if this guy, tell me if you get the same thing, I got approximately 0.4634672661. Anybody else get that? I mean, it really took me about 15 seconds to do that on a cheap calculator. So if you're taking any time to do that, you're probably not doing it correctly. I mean, there's only a few buttons to press. And then the next one, again, be in radian mode.
Yes.
Okay, shift. This one's approximately 0.463647609. Well, those are obviously very, very, very not. Wait a minute. I only did 4 terms of the Taylor series, and how good is this?
It's 1/10, it's accurate to the 1,000th.
Yeah, that's pretty cool, huh? Well, what if I need more accuracy? What's always the answer?
Add more.
More terms. And if I keep going, what's going to happen is, let me zoom back out again. As I keep going, the blue and the red ride for longer periods of time. Is everybody okay with that statement then? Okay, so we've just derived a power series. Okay, it's called a power series because of the form. How we derived it by taking derivatives, it's more specifically a Taylor series, because it's a power series that was generated by taking the derivatives. But remember, we could just make up a series. It didn't come from any particular function, but we could just make one up. But this one's very specific. This is beautiful, okay? Now, why are we doing this? Because I want to do something totally different. I want to take a limit, okay? And let's suppose I wanted to do the limit, let's say as x approaches 0, okay? Of the inverse tan x over x. Now, we learned how to do limits in Calc 1 for trig limits by using the fact that sine x over x approaches 1 as x approaches 0. You know, we used facts like that. But that was for the trig functions. This is an inverse trig function. So none of the algebraic manipulation we did in Calc 1 will help us here. That won't work, because that only worked on sines and cosines and tangents, not inverses. Well, tell me a way I could do this. Numerator and denominator both tend to what? They both tend to 0, don't they? So this is an indeterminate form of 0 over 0, so what can I use?
L'Hopital.
I can use L'Hopital's rule. And besides, by the way, right now, at this moment in time, that is the only way we know of to do this problem. Okay? What's the derivative of inverse tan?
1 over
1 plus x squared.
And then the derivative of x is just
1.
1. And what will this give us?
1 over 1.
1. Okay? No, hold on, that's not what I wanted to do. Okay, this is not cooperating. Hold on. All right. There we go. Okay. I don't like that I have to enter it as arc, but that's the only way this will accept it. Now, just stare at this for a moment. We know that inverse tan is defined for all real numbers, right? The domain is all reals. So inverse tan over x is not defined for all reals, it's defined for all reals except 0. Well, there's only 4 types of discontinuities, right? There's removable, there's asymptotic, there's break, and there's endpoint. Well, we know it's not endpoint because it's defined over the whole number line to begin with, so that's out. If it was a break, would we see that clearly?
Yeah.
How about if it was asymptotic? Wouldn't we see that clearly? We'd see things going off to infinity. Therefore, what's the only one left? Removable. Would you see removable? Do you see a point removed from a graph? No, you can never see a point. That's why when we illustrate it, we always put a little open circle. It has to be removable. Didn't we just say the limit was 1? Doesn't that look like it's passing through 0, 1? It's not passing through 0, 1, but there's a removable discontinuity at 0, 1, isn't there? Huh, that's interesting. Okay. I shouldn't have erased all this. I just did a moment ago. You're going to like this next part. This is really cool. What I'm going to show you next actually isn't in most textbooks, unfortunately. Okay, so we know this. We just did this a moment ago, all right? So here's what I want to do. I took our Taylor polynomial and I just put it over x, because we know that inverse tan over x, that's the limit I want. But what if instead of asking inverse tan over x, I did polynomial over x? Do you notice anything on your graph there, right around there? Doesn't it kind of look the same? In other words, doesn't it look like 0, 1 is there? So I'm going to show you something you may never realize. Most of the limits that are indeterminate forms that we've done in the past, the 0 over 0 or infinity over infinity indeterminate forms, you don't actually have to do L'Hopital's rule. Now, many of you like L'Hopital's rule, but L'Hopital's rule involves derivatives, and could you imagine taking a limit and never having to take a derivative? Think about that. If I took a limit but didn't have to take a derivative, that might make the limit itself a little bit easier. So how could I do such a crazy thing? Oh, there's my eraser. Let's go back. Now, what is this? Well, if I wrote the first few terms there, we just did this. I just want to make sure we just did this a moment ago. This pattern continues forever. Do we all agree with that? I want to now do inverse tan x over x. I don't really want to rewrite this. I really want to rewrite this. What would I get? Would I get the same thing, but all my exponents reduced by 1? Okay, mathematically is that true? I haven't done any calculus yet. All I did was I restated the Taylor series, but I divided by x. So now if I wanted to do the limit as x goes to 0 of inverse tan x over x, wouldn't that just be the limit as x goes to 0 of all of this gobbledygook? I'm going to rewrite it one more time. By the way, is it legal to put plus dot 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 and not put any more terms?
Yes.
Why?
Because
What's happening to my exponents, first of all?
They're
growing.
They're getting bigger. And x is approaching 0. So isn't every term after this, forever and ever and ever, isn't every one of those terms going to approach 0?
Yeah.
Yeah, so do I need to keep writing is the question. No. Can you evaluate this limit?
Yeah.
1.
Well, that's kind of cool. We got the same answer, but algebraically, it's actually a lot easier. And there were no derivatives involved. Oh. Well, I know how to take the derivative. Yeah, but inverse tan's derivative, some people might forget. But everything we've said is absolutely correct. Inverse tan x over x is equal to this. And now I can take the limit. It's crazy. So what we want to do for the next few minutes is do limits using the Taylor series rather than actually do L'Hopital's or even algebraically. Now, if it were a limit of a polynomial over polynomial, no, we'd just do the limit like we normally would, because you're not going to write a polynomial as a series. A polynomial can be written as a series. Let's say I have a quadratic. So I have an x squared, an x, and a constant. How would I write it as a series? Well, I could. It's just that everything after x squared would have a coefficient of 0. That's kind of boring, isn't it? There's no x cubed, x fourth, fifth, sixth, on and on and on. So you don't write a polynomial as an infinite polynomial. You write transcendental functions as infinite polynomials. Okay? So, one of the most important limits that exists, the one that all of the trig limits are based on, you guys did this in Calc 1. This is what? So we had one also look like a cosine, right? 1 minus cosine x over x, and that limit was 0. That's where we got all of the trig derivatives from, because then when you did the limit expansions of the trig derivatives, you got one of these statements in there. So let's go look at this one. Oops. Okay. Now, in Calc 1, I will do this. I will do the demonstration graphically. Again, sine x is defined over the whole number line, so sine x over x is defined for all real numbers except 0. There's no break, we can see that. There's no vertical asymptotes, we can see that. There's no endpoints, we can see that. So the only thing left actually is simply a removable discontinuity, and we suspect it's right here, because didn't we know this was equal to 1? What I'm showing you does not constitute a proof. No, we actually do the proof. How many in your class did the proof of this using the squeeze theorem? Because you're in my class, okay. You use the squeeze theorem. What you do is you have two triangles and then you have the arc in between, and you actually, it's a fairly simple thing to do, but you use the squeeze or sandwich theorem to prove this. It actually needs to be proven. I'll demonstrate its truth, but this isn't a proof. We actually do a formal mathematical proof. It's 100% geometric. But now that we know things like L'Hopital's rule, we go, oh, I can just do derivatives. Let's do this using series. So last day, I believe, I told you guys, we derived cosine, so I told you sine because the derivation is almost identical. Remember, the cosine looks just like this, except it's 2n rather than 2n plus 1. Which means that the cosine only has even powers of x in its expansion. The sine only has odd powers of x in its expansion. So we know this one's going to look like x minus 1 over 3 factorial, x cubed plus 1 over 5 factorial, x to the 5th, minus 1 over 7 factorial, x to the 7th, and so on. We know this is true, okay? Then what about the sine x over x? Using the same reasoning. Again, I can do it from here. All I have to do is decrease this by 1, by the way. That's an easy thing. But does that help me when I'm going to take a limit to write the power series? No, I need to see the terms themselves. It is absolutely correct for you to say that this is equal . This is absolutely correct. But we're going to take a limit in a moment, and I don't think that helps, because I don't know what any of the individual terms are. Oh, so can I just take all of this and divide everything by x?
Yeah.
So that would leave me with what?
1 minus 1 over 3 factorial x squared plus 1 over 5 factorial x to the 4th minus 1 over 7 factorial x.
Yeah, and I think we all agreed that I don't really need to do any more terms because my exponents are growing without bound. So finally, if I want to take the limit as x goes to 0 of sine x over x, then I'm taking the limit as x goes to 0 of this. And all that would leave me is 1. That is cool, isn't it? Let's do a slightly different one this time. What if I wanted to do the limit as x goes to 0 of sine of kx over x? K could be any real number. K is not 0, though. That would be boring. Well, I absolutely can use L'Hopital's rule. So if I gave you a specific value for k, you could manipulate this. I'm going to show you how we do it in Calc 1. This is exactly how we do it in Calc 1. True or false, what I just did? I can almost take the limit. Clearly, kx is my theta. But I don't have theta going to 0 yet. Wait a minute. If x approaches 0, then tell me about kx. Doesn't it also approach 0? So can I write kx here? Yeah, I actually have to. Oh, what is that limit right there that I boxed? That equals 1. So my answer is k times 1. Now, if I use L'Hopital's rule, am I going to get the same answer? Because if I use L'Hopital's rule, I'm going to get cosine kx times k, and that's where that's going to show up in the answer. Okay, this is the Calc 1. Calc 2, we would use L'Hopital's rule. But now let's do it using the Taylor series. But that means I have a completely different Taylor series this time. What would the Taylor series for sine kx be? Now remember I showed you guys last week, if that's thing, then thing shows up right here. So what's thing in this case? Kx. So what's going to show up right here?
Kx is equal to n plus 1.
So far so good? How does that affect the k? Or do I even have to worry about how it affects the k? Can I be really lazy and just write the same expansion, but replacing my x's with
Kx.
kx's? Would that work?
Yeah.
Yeah, it would work. So this would be kx minus 1 over 3 factorial kx cubed plus 1 over 5 factorial kx to the 5th and so on. Okay? So then sine of kx over x, oh, now I gotta deal with the k's, don't I? So that would be what? K minus, how about if I write that as k cubed over 3 factorial x squared, would that work?
Yeah.
Plus k to the 5th over 5 factorial x to the 4th, on and on, on and on forever. Now I want to take the limit as k approaches 0, excuse me, as x approaches 0, then all of these terms are going to approach 0, aren't they? Leaving me nothing but k. And isn't that what I'm supposed to get?
Yeah.
Yeah. But we didn't do a single derivative here. We didn't use any calculus. We just used a little bit of algebra. In fact, we didn't even use anything about the sine function in general. We just used the Taylor series expansion. So if I didn't even know what a trig function was, but I knew the Taylor series, I can do these limits actually pretty simply. Now, there's another limit in Calc 1 that we show. And some would argue this is the most important of them. I don't know if I say it's the most important, but it certainly is a really important one. Where would this one come up? I'll remind you where this one comes up. This one comes up if I wanted to differentiate e to the x, and I'm using the definition of the derivative, if you remember. It's e to the x plus delta x minus e to the x. Sorry, this is a little hard to read. Okay, that's the definition of the derivative. And then what we did was we factored, actually, let me just for a moment. I don't know that I'm going to need Desmos anymore. Because the limit of a product is the product of the limits. Now, that's easy. There's no delta x in that. That's e to the x. What we demonstrate, and I will do it by using Desmos and again showing you the graph. And so when I draw the graph, I'll draw the graph of e to the x minus 1 over x, because my argument is the thing that's approaching 0. Got it? Now we demonstrate that that part is 1. We demonstrate it, we don't prove it. Because the proof requires L'Hopital's rule, actually. So we only demonstrate this limit in Calc 1. We demonstrate that this limit is 1, thereby the derivative of e to the x is e to the x. But I want to use limits once again. Okay? So that when I said this is one of the more important limits, you notice the argument is approaching 0, e to the argument, argument. So in fact, it's a delta x over here. You know, it's like calling the sine function a theta. It just, the thing that's going to 0 is showing up in the denominator and in the exponent. So, how do I use the Taylor series? Well, e to the x is probably the most important of all the series, and one of the easier ones to remember, as it turns out. So if I wrote down the first few terms, it's going to be 1 plus 1 over 1 factorial x plus 1 over 2 factorial x squared. We'll just write a couple more. A couple terms. Plus 1 over 3 factorial x cubed forever and ever and ever. Therefore, e to the x over x, I can change that to an n minus 1, and that would be correct. But again, it's hard to see what I'm taking the limit of unless I actually do it on the expansion part. So what is this going to be? Did I lose? Oh, I'm sorry. E to the x minus 1, sorry, over x is going to be this. Minus 1. I know that looks kind of goofy on top, but these are growing, these exponents are growing without bound. But the minus 1 on top means I'm going to cancel those guys. Oh, and now I'm going to have everything on top has at least an x to the first power, doesn't it? So when all is said and done, what will I have left?
1 plus.
We'll just call it 1.
1 over 2 factorial x plus 1 over 3 factorial x squared, so on and so forth.
And now I want to take this limit as x goes to 0.
Yeah.
You like that?
Yep.
Isn't that cool?
Yeah.
The one beautiful thing about the Taylor series, as long as I'm doing things close to the expansion point, and by the way, all these problems we're using a 0, because it just makes a lot more sense to use a 0 to expand, because I know all the derivatives evaluated at 0. The exception of all of the power series that we will derive is the natural log. That's really the exception. All of those have to be evaluated at 1, but that's not even a difficult thing. So here's an example of how we can use the Taylor series to do limits. And there was no calculus involved. All I did was restate the series and then manipulated it algebraically, like in this case, you know, subtracting 1 and then dividing everything by x. Think about that. It's kind of cool, isn't it? Now, I want to do one more, because it's the only other limit you did in Calc 1, and it's the one involving cosine. This is the other one. You do sine x over x and 1 minus cos x over x, and then when you do your expansion later on. And by the way we proved this one, lest you forget, we proved this one in Calc 1, no cleverness involved. We only use the fact that we know that sine x over x approaches 1 as x approaches 0. So then we go like this. I'm going to multiply numerator and denominator by the conjugate, which, by the way, x is approaching 0. So 1 plus cos x is actually approaching 2. So that's totally legal. And now on top I have 1 minus the square of the cosine function, and on the bottom I have x times 1 plus the cosine function. So now what do I have on top? Isn't that sine squared? By the way, this is still an indeterminate form. Numerator and denominator are still approaching 0. So now I use the fact that the limit of a product is the product of the limits. Again, this is Calc 1. If you're wondering when in Calc 1, well, in my class, this is probably the 4th day of class. I mean, this is really, really early on in the semester. We haven't even defined the word derivative yet. Derivative hasn't even shown up yet. So what if I wrote it like this? Is that correct? The limit of a product is the product of the limits. What's that one? 1. As x approaches 0, my denominator is approaching 2, but my numerator is approaching 0. So we know that limit is in fact 0. Okay, everybody with me in that? So let's do this as a series. And finally have an answer that's not a 1. This will be our last one. So the cosine function so this one's going to be 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4th minus 1 over 6 factorial x to the 6th, forever and ever and ever. I now want to do 1 minus the cosine function all over x. Well, it's going to be all of that. Oh, it's going to be 1 minus all of that. Oops, factorial x to the 4th minus 1 over 6. Can we reduce this without rewriting it multiple times? Well, first of all, I got to distribute that negative sign, but the ones are going to cancel, aren't they?
Yeah.
So on top, I'm going to have a positive 1 over 2 factorial x to the first power, then minus 1 over 4 factorial x to the third power, sorry, that's x there, and then plus 1 over 6 factorial x to the 5th power, forever, never, never. Actually, I should put a minus here. Okay. So the power series for 1 minus cos x over x looks like this forever, never, never. I now want to take the limit as x approaches 0. But every single term has an x in it, doesn't it? So therefore that limit will be 0. Again, confirming what we already knew. You gotta admit, it's kind of cool, huh? Okay, so here's a very simple but really powerful application of using the power series for limits. Because what if it were more complicated? So, well, what do I mean by what more complicated? I could just use L'Hopital's rule on this one. Yes, you could use L'Hopital's rule on this one. Yeah. You want to use L'Hopital's rule on this one? Not so much. In other words, writing the power series for this, piece of cake. Doing derivatives of this, yeah, a little bit ickier. Now, I'm not saying it's hard, but it can get really icky really fast. Think of the e to the x if I now make it e to a power other than x. The power series was simple. Right? I just replace x with the new term, right? Thing. And then everything else falls in line. So depending on the complexity of the question, it can actually be far easier using the series to find the limit than any other technique. Now, you have techniques and they're still valid and they always work. But you've got some alternatives now. We just did sine x over x technically 3 ways. We did the algebraic approach we learned in Calc 1. We used L'Hopital's rule. We used its Taylor series. Cool. All right. Totally different thing now. We change gears. Okay, I just want to remind you of something that you know you've used before, but not a whole lot. In derivations in Calc 1, we've done this before. So, I want to do the binomial expansion. So I'm looking at a plus b to a non-negative integer exponent. What do we get? Well, we get 1, we get a plus b, we get a squared plus 2ab plus b squared, we get a cubed plus 3a squared b plus 3ab squared plus b cubed. Can we do this forever and ever and ever? Mm-hmm. Yeah. If I look at the coefficients only, it builds kind of a cool little tree here. If I do this forever, we have a name for this. You guys remember what it's called? Pascal's triangle. Pascal's triangle gives me all the coefficients as I go. But the problem is Pascal's triangle is not a very simple recursion. You see, I want to use Pascal's triangle. Can I tell you what the next row is? Okay, I'm going to go out on a limb. I'm going to do my part. Okay. I'm pretty sure that's correct. What do you think, Max? What do you think goes there?
4.
How about here?
4. 6.
And where'd you get the 6?
Add 3 and 3.
Yeah, you always add the 2 because it's offset. So I want to find the coefficients of a plus b to the 12th power. That's a lot of rows I have to complete first, isn't it? In other words, this is not a very good recursion. I want to find the coefficients of a plus b to the 100th power. I'll get back to you later on that one. Do you understand that that's not efficient, right, to find them this way? I just know that's what they are. What's more important is to be able to determine how are these calculated. Well, we know they are combinations, okay? So if it's a plus b to the n, and I want the coefficient, at some point there's going to be an a to the k, b to the n minus k. I know that because the exponents have to add up to n. And the coefficient for this, n choose k. Okay. This is what we know. This is why you learn this in algebra, why you use it in statistics. We actually use it in Calc 1 to derive the derivative of x to the n, because we have to do x plus delta x raised to the nth power, do the expansion. It's kind of nasty. What is n choose k again? Do you guys remember?
N factorial over n minus k factorial k factorial.
Now, that's well and good, but then it gets kind of complicated. I would rather do this a little bit differently. Everything we've said is true and correct, but I want to write it slightly differently. So I'm going to do it like this. I want a plus b, I'll just say to the kth power. I know my first term is a to the k. I know my last term is b to the k. Do y'all agree with that?
Yes.
This term is going to be k a to the k minus 1b. And this one's going to be also k a b to the k minus 1. That's all well and good. I'm really interested in this end. I want to write the first couple of terms down here. So when you're doing something like this, let's just say hypothetically it was, let's do it simple. I have 10 choose 7. I don't have a calculator. Now, I think I've discussed this with you guys before, right? I've taught the math portion of the GRE test, and they have to do things like this without a calculator. They get the little one on the screen that adds, subtracts, multiplies, and divides, as long as the numbers are really small, no order of operations, no exponent key, certainly no factorial key. I have to calculate this without a calculator. Well, I do know it's this. I do know it's this. How do you do this without a calculator? Sorry. I sometimes forget to mute that.
You would.
How do I do this without a calculator? Well, true.
Yeah.
Can I now do this?
Yeah.
Yeah. What's the answer going to be? I can keep canceling, or you can just multiply. So it's 720 divided by 6, 120. But that's way easier than trying to calculate the factorials. Do you agree? So in other words, what is this? How about if I wrote it as 10 times 9 times 8 over 3 times 2 times 1? That's really what or better yet, not even 3 times 2 times 1, just 3 factorial. Because that's the smaller factorial. I can deal with that. So here's what I want to do. I want to do the same thing here. What's the next term? Isn't it k choose 2? Which would be k times k minus 1 over 2 factorial. Why? Because I then canceled all of the other factorials. That's what we just did here. Let's do one more term. What's the next term? K minus 1, k minus 2 over 3 factorial. That's exactly what this is right here, right? 10, 10 minus 1, 10 minus 2. Okay? A to the k minus 3, b to the third. Now, I'm going to put plus dot dot dot. It's going to keep going until it's done. Do you agree with this statement that I have right here? You should, because it's true. Let me throw a what if at you. These have to be non-negative integers. because I can't have a 0, as boring as that is. What I just wrote is true for all real numbers, k. Well, no, not for all real numbers, k, but certainly for all rational numbers, k. What if k was a fraction? That's still true. What if k was a negative integer? That's still true. The big difference, if k is a positive integer, then there is a last term, right? The b of the k term. Everybody okay with that? Why? Because at some point I will have no more exponents. There is a last term. When I do a plus b to the 10th power, there's no exponents bigger than 10. But what if I did a plus b to the 3/2 power? I'm never going to have exponents of 0, am I? Oh, so that means that this sum would then be infinite. We're taking our binomial expansion of happy things, and we're going to look at it as if, what if I have exponents that are not non-negative integers? Very specifically, two types of exponents. What if my exponents were halves? What if my exponents were negative integers? Turns out this will still be true, and we're going to generate the power series that way, which is very cool. So now we're actually going to simplify this tremendously. And here's how we're going to simplify it. Okay? I just showed you the expansion. That's the expansion for a plus b to the k. That is absolutely correct. Now, I'm going to let a equal 1 and b equal x. So now the expansion for 1 plus x to the k. What would it be? Well, if a is now 1, that's just going to be 1, right? And then what's the next one going to be? K times 1 times x. Pretty sure that's kx. And then the next one's going to be k times k minus 1 over 2 factorial times x squared. And then k times k minus 1 times k minus 2 over 3 factorial times x cubed. And this is going to go on and on and on. Wow, this sure looks like a power series to me. Look like a power series to you?
Yeah.
Yes, it's the binomial expansion of a power series. Does it apply to any of the things that we've looked at before? No. No, it only applies to things that can't be written in this form. Okay? So have we done a lot of these? No. All right, sine x and cos x don't look like that. E to the x doesn't look like that. But if I have anything that looks like this, crazy. So let's do an easy one. Let's start with easy. Let's do, how about 1 over 1 plus x? First thing I want to do is write that as 1 plus x raised to what power?
-1.
-1. I need to write it in that form because I need this. So when I start this expansion, my k is clearly then -1. This isn't a normal binomial expansion because the stuff came from a denominator. Well, according to this formula that we just spit out, what will we get? Well, let's write down the first few terms. We're going to get 1 plus -1x. Then what? Plus -1 and then subtract 1. So -2 over 2 factorial x squared. And then -1, -2, -3 over 3 factorial x cubed. I want to do this, I'd really like that, right? I'm going to put dot, dot, dot. If I can figure out the coefficient of this term, then I can write the power series. Well, this is one of those times maybe it would be a good idea to actually simplify the coefficients. So this is 1 minus x. What does that reduce to?
X squared.
-2 factorial over 2 factorial. So it's -1.
Isn't that just positive 1?
Right.
Does everyone say that's just going to be a 1? I'm saying, what does it reduce to? I think it's just 1. Okay. How about the next one?
Negative
one.
x squared.
You think? I don't know, guys. I don't know, is it obvious or is it not obvious? 1 minus plus minus plus minus plus minus. My coefficients are just ones, negative. What's going to be the coefficient of x to the n? Oh my goodness. Are you serious? Is it actually that easy? I don't know if I wrote it differently. What if I wrote it as this one only this one? Is that the same thing? So was this just a simple geometric series where my r was negative x? And isn't that what it would look like if my r was negative x at the other end? You're like going, oh. No, that's just this one. This is the only one I could do that on. So I used one where we actually already knew the answer to this one. If we looked at it in this form, we would have written this. But I'm showing you this is the derivation, and the derivation was actually kind of simple for a couple reasons. One is it's just a simple formula. It's a plug and chug. How many derivatives did we take in this process? How many derivatives did we take in this? None. Yeah. We didn't take any derivatives. We wrote down the power series without doing any derivatives. Ooh, worked out very nicely. So let's do a different one, okay? Maybe let's do one where it's, how about 1 plus x to the, or 1 over 1 plus l, right, like that, to the third power. Well, first thing we're going to do then is rewrite this as 1 plus x to the negative third. Now, can I use the geometric series here? No, that exponent kills it. No, but we're going to use this expansion right here. So this is going to be 1 plus negative 3 times x plus negative 3 times negative 4 over 2 factorial x squared plus negative 3 times negative 4 times negative 5 over 3 factorial x cubed, on and on and on and on and on. Okay. Now, I can absolutely simplify all of my coefficients. I'll do one more. Negative 3, negative 4, negative 5, negative 6 over 4 factorial x to the fourth. It is absolutely correct to simplify my coefficients. The question is, should I? Well, if I simplify them, then this is 1 minus 3x, 12 over 2 plus 6x squared. That's 60 over 6 minus 10x cubed. That one's going to be plus 15x to the fourth. And this is absolutely correct what I just wrote. 1, 3, 6, 10, 15. Do you see a clear pattern of your coefficients here? Some of you are nodding, some of you are shaking. I'm shaking my head. I don't see a clear pattern of your coefficients. I don't see factorials. I don't see exponentials. This is correct, but do you see a clear identifiable pattern of your coefficients in that form, other than they're alternating in sign?
They're increasing by an additional 1 each time.
Yeah, the problem is writing that as a formula for the nth term.
I see what you mean.
Yeah, no, he is correct. I added 2, then 3, then 4, then 5. That's correct, but trying to write that as a formula, yeah, I really can't write that. So this is one of those times maybe I shouldn't simplify. So let's go back to the original. Your denominators are clearly growing. That's kind of the no-brainer. But the question is, what is, well, I think I'm going to have a negative 1 to the nth power because, right, there's the same number of negatives as there is exponents. So it's going to be negative 1 to the n, and my bottom's definitely n factorial. The question is, what's the top? Well, it's 6, 5, 4, 3. I'm missing the 2, 1. It's 5, 4, 3. I'm missing the 2, 1.
Can you write as a factorial and then divide the 2?
That sounds like a really good idea, Chase. What if I went times 1 times 2 and then times 1 times 2? Would that be legal, first of all? then wouldn't my numerator always be a factorial also? What factorial would it be exactly? If that's n factorial, then what's this going to be? N plus 2 factorial. You with me so far? But you know what? I think I can improve upon this. I don't think I would have seen it when I wrote it out in green over there a moment ago. I think that was green. Was that green? That was green, right? Okay. Could be. When I wrote that out, I said it wasn't obvious what the pattern was. But I think now it might be. Can I write my top as n plus 2, n plus 1, n factorial, and the bottom is 2 times n factorial, which is not 2n quantity factorial? Can I do that? Would that be a simpler representation? The answer is yes, it would be. Now, what were the numbers we had a moment ago? It was 1, -3, 6, -10, 15, and so on. Oh, but now I can look at this as what? 3 times 2 over 2. 4 times, see, hold on, where are we now? 3 times 2 over 2. 4 times 3 over 2. 5 times 4 over 2. 6 times 5 over 2. Does everyone see that now? There actually was a pattern. We just didn't see it because who would have thought to double all those numbers? If we had doubled those numbers, we might have seen the pattern. But that's the pattern. N plus 2 times n plus 1 over 2. So now, can we write this as a power series? Yes, we can. N equals 0 to infinity, -1 to the n, n plus 2, n plus 1, all over 2, x to the n. Now, is this the only way to get this answer? No. We could have treated this as a Taylor series. Looking at the form of my answer, what did we expand about, by the way? What number? It's x to the n. So what did we expand about? 0, because it's x minus 0 to the nth power. So I could have taken many derivatives of this, and that would have been not that hard, by the way. Take your derivatives, evaluate each of your derivatives at 0, look for a pattern of the coefficients, and then write the series. That's exactly how you would have done it an hour ago. Right? But this is actually, for this problem, much, much, much easier, isn't it? Much easier. Because I didn't have to take any derivatives. Do I still have to see a pattern with the coefficients? Yes, if I want to be able to write my answer. This is called a closed form. Most textbooks do not have closed form answers. In fact, most textbooks for this chapter or this section have no closed form answers. They write all of their answers like this plus ... Which is not wrong, but it's not entirely useful. Let's say you had to do some programming. You had to write this and you had to calculate. How do you tell the computer plus ... No, you just have to enter a lot of terms, and then that's as far as the computer can calculate, because the computer's not going to guess what the next term was. I need an actual formula, summation formula, and that is not always possible, just so you know. My Math 255 class is doing a lot of the same kinds of stuff. Their stuff is a little gnarlier, and finding clear recognizable patterns, they're not so many, okay? What is a pattern that I recognize? We talked about this before. Usually the two that I want to be obvious are the factorial patterns, the exponential patterns. When I have those, life is much, much easier, because then it's easier to set things up. Canceling is really nice and so on. Now, I want to do some halves. Halves are the ugliest ones, because the pattern of exponents is not clear, it's not always obvious. So I'm going to show you a really cool identity that unfortunately I've never found in any textbook. I learned this, I don't know when, I don't know where. I think it might have been Professor Newton back when he was showing me his stuff. You know, way before the Apple thing. He was never the same after that, that concussion. People don't realize it was a concussion, and then he came up with all those weird laws and stuff. Okay, what if I had a pattern of fractions and I'm trying to see something? So here's what I'd like you to do. I would like to multiply the first n positive integers together, and I would like to come up with a formula for this. I believe I have this in the notes, but take good notes because I don't believe this is anywhere. I don't believe there's anything published that has this anymore. 50 years ago, maybe there was stuff. There's information that used to be in textbooks that's just not there anymore. I don't know why. I've never seen this in any calculus book, yet it only occurs in calculus. Do you see a clear pattern here? Well, yeah, 2, 4, 6, 8. Yeah, but I want an answer. What if n is 1,000? Do you really want to multiply 1,000 numbers together?
No.
No. I want a simple formula. Well, let's be clever. How about if I thought of this as 2 times 1 times 2 times 2 times 2 times 3? Is that a true statement mathematically? How many numbers do I have altogether?
N.
N.
So 2n factorial.
2 to the n factorial.
1, 2, 3, 4, up to n. There's my n factorial, and then I had n2s. You like that? Now, let's, just to be certain we did it right, I always say it's a really good idea to check. Let's, by hand, 2, 4, 6, 8, oops, 2, 4, 6, 8, 10. Okay? Do that on your calculator. There are 5 numbers, so it should be 2 to the 5th times 5 factorial. Do both of these on your calculator. This is the easiest way to check. I don't need to test every number, but I want to make sure I wrote it down correctly. This is why I always tell people to do a quick check of just a small quantity. Okay, what do you get in both cases, I hope?
3,840.
Did you get that for both of them?
Yes.
Okay, that means we didn't mess it up. That's a really cool formula, and that was really easy to use, and now you're never actually going to see that one. No, not that one. You're going to see this one. The first n positive odd integers. This is the one that you're actually going to see. Well, I'll just do what we did before. I'll, factor out the 2's. Oh, wait a minute. Can I make this into factorial? No. Ah, darn. No, I have an idea though. Let me write this a little bit differently. What do you think? It's still the same thing. It's not the 2 to the n that allowed me to make that one easier. It was the ability to write it as a factorial. If only this were a factorial. Well, it can't because what's it missing? All the evens. Well, I think I left enough room for you guys to write the evens in there, didn't I? Okay. I just wrote all the evens in there, so now it's what? 2n quantity factorial. Well, can you just do that? Yeah.
If you divide it by.
If you also do it down here,
Just 2n factorial over 2 to the power of n factorial.
you slow down, Chase. 2n factorial over what?
2 to the power of n times n factorial.
Yeah. And that turns out to be a really powerful and really important formula that only is going to occur when you're multiplying odds. And specifically, you're going to be multiplying odd fractions. Now, let's do what we did a moment ago. Let's do a quick test just to make sure. Let's do 1, 3, 5, 7, 9. The first 5. So my n is 5. I want to compare that to what? If n is 5, then what's that? Is it 2 times 5 factorial? No, it's 10 factorial over 2 to the 5th, 5 factorial. All right, let's do both of these on our calculators. Again, I want to make sure I got it right. It is possible that you could have something a little bit off. That's always possible.
Both are 945.
What is it?
Both are 945.
945, is that a good thing? Yeah, that means I got it right. The crowd goes wild. Well, not yet. That's just more of a, okay, we didn't mess it up. If I have a pattern of evens or a pattern of odds, what I just did was I wrote it as what's called a closed form. I don't have to put dot, dot, dots. If I asked you to multiply 1,000 integers together that had a pattern, you really don't want to write them all down. You'd rather just go to something that looks like this, right? It's immediate. I have technology on my side. It's not the size of the numbers that I'm concerned with. All right, so let's do the following. Now, I could do this as a Taylor series. There's nothing wrong with that. It's not geometric because of the square root. Would those be hard derivatives to take, by the way? I have 1 plus x raised to a power. Those derivatives, and all my chain rule factors would be 1. Those derivatives would be easy. I evaluate them at 0, it's easy. But it's the pattern of coefficients that I still would have to recognize. So I want to use the binomial expansion because it's actually faster. It'll give me the exact same answer that the Taylor series expansion would be, exactly the same. I just don't have to take any derivatives. I'd rather do that. But I first have to rewrite this how? To the what power?
To the 1/2 power, or negative 1/2 power.
That does matter. By the way, positive 1/2 is also a valid question, but this is the negative half. You always rewrite it for the simple reason you want to make sure you have the right value of k. If k is supposed to be negative and I have a positive number, I give a completely different answer. Okay? Well, according to what we just did, what should this be? 1 plus negative 1/2 x plus negative 1/2 times what? Negative 3/2 because I'm subtracting 1. Okay? I'm not sure how many terms I need to write, so let's put just a few. I'll do one more. That's not the last term, no, it's a plus dot, dot, dot now. Ugh. So probably the most